Question on number 21 here, and I just got done making the video for problem number 19, and I'm guessing you might have just done 19 yourself before you got to 21. Now, the method that I showed you guys in class and the method that I did here in number 19 doesn't really work very well for problem 21 because we're now dealing with a quadratic expression inside the absolute value. So I'm going to approach this one a little bit differently. I'm still going to approach it graphically, but in a different type of graph than what I did here on 19. This was a number line, and now what I'm going to do is I'm going to focus instead on the function here, y is equal to x squared minus 1. So I'm hoping that graphing that parabola isn't going to cause you guys any real trouble here. We've got a parabola being shifted down 1 unit, so I'm going to try to make this fairly accurate, but I'm not going to worry too much about it, guys. And here we go. So we're shifted down 1, so our vertex is at 0, negative 1. And then because our a value there on the x squared is 1, this is a quote-unquote normal or standard parabola, meaning from that vertex we would go right 1 and up 1 and get a point right here. Left 1, up 1 would get us a point right here. When we go right 2 units from the vertex, we're going to go up, we are going to go up 4 units. That's what I meant to do. Here we go. We would go up 4 units from that vertex right there because 2 squared is 4. So here we go then. From the vertex right 2 would get me here, but then up 1, 2, 3, 4, we get a point right here. And again, symmetry with respect to the y-axis. So this is what our ooh, that was ugly. This is what our parabola looks like. And of course, that graph isn't perfect, but it should be good enough. We want to know, everybody, when is the value of this function right here greater than or equal to 2? Oops, hang on a second though. I ignored the absolute value, and that's really important as well. So what I've graphed here so far is just y equals x squared minus 1. So now let me shift colors. I'm going to go to purple on you here. And this is a good skill for you guys just to have in the vault here at some point. How do we take a graph that we know and graph the absolute value of that function? Well, let's go back to what we already know about absolute value. You can completely ignore absolute value when what you're taking the absolute value of was already positive. So if we take a look at the blue graph, this graph was already positive here and here. So those parts of the graph aren't going to change at all when we apply the absolute value to it. However, there was a part of this graph right here that existed below the x-axis, meaning that those y values were negative. And what do you do to negative values to take the absolute value of them? You simply take their opposites and you turn all those negatives positive. So what we're basically going to do here, guys, is take the bottom half of this graph and flip it upwards now over the x-axis. So let me clean this up just a little bit and say that essentially then my new graph is going to look something like this. Okay, so now I'm going to get rid of the blue parabola here. Okay, yeah, in fact, I think we can just wipe that guy out and say, all right. What we're dealing then with in purple there is the graph of y equals the absolute value of x squared minus 1. So that's kind of a quick little trick right there for how to take an absolute value graph of something that you already knew. Now we want to know, back to where I was a moment ago, we want to know when or where really is the value of this function greater than or equal to 2. Now remember, this is a y value right here. So if I went to the line y equals 2, that would be this line, horizontal line right there. That is y equals 2. And the question now becomes, for what values of x is the value of that purple function there greater than 2? Or above that red line that I just drew. And as I think you guys can see, that's going to happen on this interval right here. That part of the purple graph was above that red line, and this interval right over here. Everywhere that I didn't just shade, which is effectively right here, all of these y values now are less than or equal to 2, but we only want the ones where it's greater than. So what we need to find right now then is the points of intersection, and two of them, right? This point right over here and this point right over here, where the purple graph actually hits that line of y equals 2. And it wasn't an accident that I drew them as open dots, because we just want to know where is this thing greater than 2, not greater than or equal to. So off to the side, let me just solve the equation here. X squared minus 1 is equal to 2, where x squared is equal to 3, which means that x is plus or minus the square root of 3. So I'm going to describe this interval right here, guys, as the interval starting at negative infinity and ending at negative square root of 3, parenthesis, because it's an open dot, or, meaning union here, a second interval right here in yellow that starts at the positive square root of 3 and never ends. So we say that it goes to infinity. And that is how I would express, let me get my directions right, that's how I would describe that set shown as a union of finite or infinite intervals. Every x value that exists either here or here should give me a true statement. Like, for example, if I were to choose 7. I think that's in that interval here. 7 squared minus 1 is 48, and the absolute value of 48 is greater than 2. But if I were to choose a number not in either of those intervals, like negative 1, that should give me a false statement. Negative 1 squared is 1, minus 1 is 0. Absolute value of 0 is 0. 0 is greater than 2 is a false statement, and therefore it should not belong in my answer here. So I feel pretty good about that answer there as well. Okay, so that's how we would handle problem number 21.